Shilpi Jain ma'am, good afternoon and welcome in this session. Ma'am, now we can start.
Okay. A very good afternoon to all of you, all those of you who have joined us this afternoon. Thank you very much for staying with us. It's my pleasure and privilege to introduce my colleague in the Purnima group, Dr. Shilpi Jain. She is currently working as an associate professor at the Department of Mathematics, Purnima College of Engineering, Jaipur. She completed her PhD in mathematics from the University of Rajasthan, Jaipur in 2006. Her MSc in mathematics and BSc also were from the University of Rajasthan, Jaipur. Her research interests are special function, fractional calculus, mathematical modeling, relativity, fixed point theory, and many, many more. She is a very active researcher involved in many projects and serving as a reviewer of many prestigious journals. She is a life member of many professional bodies. Many research scholars are pursuing their PhD under her supervision. Dr. Shilpi has published more than 80 research papers in various national and international journals of repute with SCI and Scopus indexing. Thank you very much for acceding to my request and for joining us this afternoon. Over to Mr. Noori for chairing the session. Thank you and welcome Dr. Shilpi Jain to this session.
Thank you so much, ma'am. Shall I share the screen?
Yes, ma'am.
Is the screen visible?
Yes, ma'am, it is.
Okay. First of all, thank you so much, the organizing committee of International Training Workshop on Computational Special Function and their application organized by MTTF, and especially thank to Professor Meher and Professor Sudhi Rajiv inviting me for this workshop. Today, my talk on study of fractional hypergeometric functions and their applications. This is a very basic talk about the newly researcher. And just a minute. Okay. So this is the outline of my talk. Firstly, aim of the talk, then introduction, classical beta and gamma function, extended beta and extended hypergeometric functions, introduction to fractional calculus, fractional differential and integral operators, fractional integral formulas, conclusion, future perspectives and references. The fractional calculus of hypergeometric function, just a minute, there is some problem. Just a minute. Yeah. The fractional calculus of hypergeometric function has significant importance and application in various fields of science and engineering. Here we aim to discuss on this talk, study, extension and generalization of hypergeometric functions, introduction of fractional calculus, fractional integral and differential formulas of the extended hypergeometric type functions by using the Zygomatic operators. We discuss these are one by one. In recent year, many extension and generalization of a special function witnessed a significant evaluation. As we all about a special function, this is the particular mathematical function that have more or less established names and notations due to their importance in mathematical analysis, functional analysis, geometry, physics, or other application. A special function is having a particular use of mathematical physics or some other branches of mathematics Prominent examples include of gamma function, beta function, hypergeometric functions, vector functions, and Bezier functions. Beta and gamma are the two important functions for the special function, because most of the special function are expressed either in terms of the beta function and or gamma function. The gamma function behave like a factorial for natural numbers. Its extension to the positive real numbers for modeling situations involving continuous changes with importance application to calculus, differential equations, complex analysis, and statistics. The gamma function is also called Euler integral of the second kind, is one of the extension of the factorial notation or factorial function. Using technique of integration, it can be shown, as we all aware about this, gamma 1 is equal to 1. Similarly, using a technique from calculus known as integration by parts, it can be proved that the gamma function has a recursive property if x greater than 0, then gamma x plus 1 is equal to x gamma x. Using technique, the beta function was first studied and invented by Laudard Euler, who was Swiss mathematician, a physicist, as astronomer, a geographer, a logician, and an engineer. Beta function are a special function, a special type of a function, you can say, which is also known as Euler integral of the first kind. It is usually expressed as beta xy, where x and y are the real numbers greater than 0. It is also a symmetrical functions such as beta xy is equal to beta yx. In mathematics, there is a term known as special function. This is the extended form of beta and gamma function, classical Euler beta function. This is the basic Euler beta function and gamma function. This is classical Euler beta function, which is given by beta x1 x2 is equal to integral of 0 to 1 t raised to power x1 minus 1 minus t raised to power x2 minus 1 dt, where real of x1, real of x2 is greater than 0, and gamma function is defined as gamma of x1 is equal to 0 to infinite t raised to power x1 minus 1 e raised to power minus t dt. Real of x1 is greater than 0. This is the basic definition of Euler beta function and gamma function. Now, the study of extension of the special function began in early 1990. Chaudhary and Jubir extended the gamma function in 1994 for the first time and studied some basic properties as defined in the following. Gamma of x1 r is equal to integral of 0 to infinity t raised to power x1 minus 1 e raised to power minus t minus r t raised to power minus 1 dt, where real of x1 is greater than 0, r is greater than 0. This is the basic definition of beta function, gamma function, and this is extended definition of gamma function. And in the similar manner, in the beta function given by Chaudhary et al., this is extended beta function, where beta x1 x2 r is equal to 0, integral of 0 to 1 t raised to power x1 minus 1 minus t raised to power x2 minus 1 e raised to power minus r divided by t 1 minus t dt, where minimum of real x1, real of x2 is greater than 0 and real of r is greater than 0. Now, in 2011, Ojrin et al. Have used the confluent hypergeometric function to generalize the classical Euler beta function and gamma function, which, as given by the equation number 5, gamma of r, r1, r2, x1 is equal to integral of 0 to infinite t raised to power x1 minus 1 f1 r1 r2 minus t minus r by t dt. This is equation number given by equation number 5, where real of x1, r1 and real of r2 is greater than 0 and real of r is greater than 0. The following is also the case of beta. Beta r, r1, r2, x1, x2 is equal to integral of 0 to 1 t raised to power x1 minus 1 minus t raised to power x2 minus 1 f1 r1 r2 minus r upon t 1 minus t dt, where minimum of real x1, real of x2 is greater than 0, minimum of real r1, real r2 is greater than 0, and real of r is greater than 0. An extension of extended beta function with r greater than equal to 0 is defined by, this is the definition of extended beta function. This is defined by integral of 0 to 1 t raised to power x1 minus 1 1 minus t raised to power x2 minus 1 e r1 r2 minus r t1 minus t inverse dt, where minimum of real x1 is greater, real of x1, real of x2 is greater than 0, real of r1 is greater than 0, real of r2 is greater than 0, and e r1 r2 is the two parameter Mittag-Lever function, which is also known as Riemann function. In above extension, Goel et al. Have used two parameters, Mittag-Lever function e r1 r2 z as a kernel of to modify the classical Euler beta function in terms of the integral. If we set r1 is equal to 1 is equal to r and r is equal to 0 in this equation, equation number 8, as you see the equation number 8, and if we put r1 is equal to 1 is equal to r2 and r is equal to 0, we have the relation beta 110 x1 x2 is equal to beta x1 x2. From if we put this equation in this equation, r1 r2 is equal to 1 and r is equal to 0, this we get the result beta 110 x1 x2 is equal to beta x1 x2. This is the theorem. Let r is greater than equal to 0, minimum of real x1, real of x2 is greater than 0, real of r1 is greater than 0, and real of r2 is greater than 0. Then extended beta function defined as equation number 8 satisfy the symmetric relation. As we are aware, beta function is a special type of function which is also known as Euler integral, the first kind. It is usually expressed as beta xy, and this is also the symmetrical function such as beta xy is equal to beta yx. The next result in the theorem, let r1 greater than equal to 0, minimum of real x1, real of x2 is greater than 0, real of r1 greater than 0, and real of r2 greater than 0, then the extended beta function defined as equation number 8 satisfy the functional relation, which is given by the equation number 11. The result gives beta of r1 r2r x1 x2 plus 1 plus beta r1 r2 r x1 plus 1 x2. The next result given by the theorem, let r1 is greater than equal to 0, r x1 plus s greater than 0, r x2 plus s greater than 0, real of r1 greater than 0, real of r2 greater than 0, and real of s greater than 0, then the Mellin transform of extended beta function defined by equation number 8 is given by the following result, which is given by equation number 12th. The Mellin transform is widely used in computer science for the analysis of algorithm because of its scale invariance property. The magnitude of the Mellin transform of a scaled function is identical to the magnitude of the original function for purely imaginary inputs. The Mellin transform is an integral transform that may be regarded as a multiplicative version of the two-sided Laplace transform. This integral transform is closely connected to the theory of Dirichlet series and is often used to the number theory and mathematical statistics. And the theory of asymptotic expansions, it is closely related to the Laplace transform and the Fourier transform. And the theory of gamma function and allied spatial functions. Motivated by the above work, Jain et al. Have extended Gauss hypergeometric function, confluent hypergeometric function by using above extended beta function and studies various properties of these extended function. They also studies the increasing or decreasing nature, concavity and log convexity of extended beta function defined by equation number 5, which we already discussed. This is the definition of new extended Gauss hypergeometric functions, which is defined by summation of n is equal to 0 to infinite beta of r1 r2 r p1 plus n p2 minus p1 by beta of p1 p2 minus p1 p naught n z raised to power n by n factorial, where real of p2, real of p1 greater than 0 and real of r2 greater than 0, real r of greater than equal to 0, mod of z less than 1, and beta of r1 r2 x1 x2 extended beta function. If we put r1 is equal to r2 is equal to 1 and r is equal to 0 in equation number 15, this equation, then we get Gauss hypergeometric function given by this result f110 p0 p1 p2 z is equal to f p0 p1 p2 z. We again see this result. If we put here r1 is equal to r2 is equal to 1 and r is equal to 0, substitute in this result, we get this result, this one, and this is Gauss hypergeometric function given by the equation number 16. Now the definition in new extended confluent hypergeometric function. Phi of r1, r2, r, p1, p2, z is defined as follows. This is confluent hypergeometric function which is given by summation of n is equal to 0 to infinity beta of r1, r2, r, p1 plus n, p2 minus p1, z raised to power n by beta of p1, p2 minus p1 and factorial, where real of p2 is greater than real of p1 is greater than 0, real of r1 is greater than 0, real of r2 is greater than 0, and r is greater than equal to 0. Beta r1, r2, x1, x2 is extended beta function. If we again put r1 r2 is equal to 1 in the previous result and r is equal to 0, then we get Gauss hypergeometric function, this one. If we put here r1 r2 is equal to 1 and r is equal to 0, then we get the equation number 18th, and this is Gauss hypergeometric function and confluent hypergeometric function given by the equation number 14th, which the result gives phi of 110 p1 p2 z is equal to phi p1 p2 z. The next theorem is the following functional relation holds. F of R1, R2, P0, P1, P2, Z is equal to P1 by P2, F of R1, R2, R, P0, P1 plus 1, P2 plus 1, Z plus P2 minus P1 by P1, F of R1, R2, R, P0, P1, P2 plus 1, Z, which is given by equation number 19th, and the condition which is given by this one. We get the another result by 2 phi of r1 r2 r p1 p2 z is equal to p1 by p2 phi of r1 r2 r p1 plus 1 p2 plus 1 z p2 minus p1 by p1 phi of r1 r2 r p1 p2 plus 1 z. The following some relations hold, which is given by equation number 21, where real of P2 greater than 0, real of P1 greater than 0, real of R1 greater than 0, real of R2 greater than 0, and R is greater than equal to 0, and mod of Z is less than 1. And phi of R1, R2, R is given by the equation number 22. The next theorem is f of r1, r2, r, p0, p1, p2, z function, the following result hold, which is given by equation number 23. The result gives summation of I is equal to 0 to k I, b p1 plus I, p2 minus p1 minus I plus k by beta of p1, p2 minus 1, f of r1, r2, r, p0, p1 plus 1, p2 plus k and z, and there is condition. The introduction of fractional calculus is a very important development in the field of calculus due to the fact that it is too widely applicable in many field of mathematical physics. and applied sciences. The fractional calculus operator having various special functions have been used to for modeling of system in turbulence and fluid dynamics, stochastic dynamic system, thermonuclear fusion, image processing, non-linear biological system, and in quantum mechanics. There are some important formulas which is given by the researchers in well-known researcher in 1695 to 1697. J.B.W. Leibniz mentioned in his letter to J. Wallis and J. Bernoulli about the possible approach to fractional order differentiation, in that sense that for non-integer values of n, the definition could be the following. N e raised to power mx upon dx n is equal to m raised to power n e raised to power mx. This is very well-known result. Just a minute. The another result by given Euler in 1730. D raised to power n x raised to power m dxn is equal to m minus 1 m minus n plus 1 x raised to power m minus n, where gamma of m plus n is equal to m minus 1 m minus n plus 1 gamma of m minus n plus 1. Therefore, d raised to power n xm upon dxn reduces to gamma m plus 1 divided by gamma m minus n plus 1 x raised to power m minus n. If we put this result in the above equation, we get this result. Euler suggested to use this relationship also for negative or non-integer values for n, taking m is equal to 1 and n is equal to half. Euler obtained d raised to power half x upon d raised to power x half is equal to under root of 4x divided by pi 2 upon root pi x raised to power half. If we you can see, if we take m is equal to 1 here and n is equal to half, we get this result. Now, J.B.J. Fourier in 1820 to 1822, the first step to generalization of the notation differentiation for arbitrary function was done by this scientist. J. Lobili in 1832 to 1855 was the first to point the existence of the right-sided and left-sided differential and integral through these approaches. Now, another researcher, G.F.B. Riemann, in 1826 to 1866, initialized fractional calculus, was born lately in the latter half of the 20th century. Riemann's notation is as follows with the complementary function. D raised to power nu ft is equal to 1 upon gamma nu integral of c to t minus tau raised to power nu minus 1 f of tau d tau plus psi of tau. Cauchy formula for nth derivative in complex variable is given by nth order function z is equal to n factorial j2 pi integral of f tau minus z raised to power n plus 1 d tau. And for non-negative integers, if we put n is equal to nu here, then we get d raised to power for the function tau minus z raised to power minus nu minus 1 appears instead of pole d raised to power nu fz is equal to gamma nu plus 1 upon j2 pi c integral of c to t f tau upon tau minus z raised to power nu plus 1 d tau. Since that time of fractional calculus has drawn the extension of many famous mathematicians such as Euler, Laplace, Fourier, Abel, Rivoli, Riemann, and Laurent. But it was not until 1884 that the theory of generalized operator achieved a level in its development suitable as a point of departure for the modern mathematics. By then, the theory had been extended to include operator d nu, where nu could be rational or irrational, positive or negative, real or complex. Thus, the name fractional calculus becomes somewhat a misnomer. A better description might be differentiation and integration to an arbitrary order. It is a practically impossible to name all made important contribution in construction of early stages of the building of fractional calculus. New era in the development of this branch of science began 40 to 50 years ago due to numerous application of fractional type model, and it continued up to now. One can mention a large list of areas of application as follows. We discuss some application now. The application, the first is given by the diphthong K, the analytical or differential equation of fractional order, an application-oriented exposition using differential operator of Capito type. Lecture notes in the lecture notes in mathematics 2004, Springer, published in Springer, Verlag, Heidelberg in 2010. Now the another published paper, this is very important paper, Theory and Application of Fractional Differential Equation, published in North Holland Mathematics Studies 204, elsewhere, Amsterdam, etc. 2000, published in 2006. The another paper by B. Kryakov, published in 1994, based on generalized fractional calculus and application in Harlow Longman. The another paper published on 2-Sago fractional integral operator in the class of univalent function, fractional calculus and applied analysis in 2006. These are very important paper regarding application of the function. The another paper published in 1993 by Miller KS and Ross B, an introduction to the fractional calculus and fractional differential equation in New York, John Wiley and Sons in 1993. The another research paper published in Academic Press, New York in 1974, based on the fractional calculus. This is very important paper for the beginners of fractional functions. Then next paper published in 1999 by Podolny I, Fractional Differential Equation, published in Academic Press, New York. The another important paper published in Theory and Application, New York and London, Jordan and Bridge, Science Publisher in 1993, based on fractional integral and derivatives. The one of the paper by Teniro, Machdo, J.A. Kryakovo V, published in 2011. The paper based on history of fractional calculus and published in Communication Nonlinear Sciences in 2011. The application in physics related paper published in World Scientific Singapore in 2000, paper based on application of fractional calculus in physics, and for modeling and control application paper published in Singapore in 2010, fractional order system modeling and control application, World Scientific Singapore. The another paper based on nano and cosmic physics published in 2013. The paper is fractional derivatives for physicists and engineers. This is very important paper for nano and cosmic physics, which is published in Springer Berlin Higher Education Press, Beijing in 2013. Mamikon Gwalin on fractional calculus and hidden physics. Here we consider some popular definition of fractional, differential and integral operator. Riemann, Lovelli and the Valet fractional integral operator, Altman and Sprenger in 1974 gives a definition. which is given by the equation number 25, which is 1 upon gamma alpha 0 to x minus t raised to power alpha minus 1 ft dt, where real of alpha is greater than 0. Hobart H in 1940 on fractional, integral and derivative. Quartz J Maths of Oxford give a definition which is given by the equation number 27 and 28. Siago M in 1978 given a paper on the topic A Remark on Integration Operator involving the Gauss hypergeometric function, published in Math Reports of College General Education, Casio University. In this paper, the definition is given by the equation number 29th and 30th. Siago M. Meda N in 1998 in the research paper, more generalization of fractional calculus in transform method and a special function, given by the international workshop. In this paper, the definition is given by in equation number 31. According to this definition, the result gives x raised to power minus a upon gamma c integral of 0 to x minus t raised to power c minus 1 t raised to power minus a dash f3 a dash b dash c 1 minus t by x 1 minus x by t ft dt. This is the very important result based on fractional generalization of fractional calculus, which is published transform method and special function. Now the theorem, next theorem is let x is greater than 0, a dash b dash c, d belongs to c, and real of q2, real of q1 greater than 0, real of s1 greater than 0, real of s2 greater than 0, s is greater than equal to 0, and mod of t less than 1 be such that real of c greater than 0 and real of d plus n greater than maximum of 0. Real of a plus a dash plus b minus c, real of a dash minus b dash, then the following fractional integral formula hold true, which is given by equation number 33, where 3f3x is a special case of generalized hypergeometric function with p is equal to q is equal to 3 in equation number 8, which is we already discussed in the equation number 8, and we gives the result in equation number 33 if we put p is equal to q is equal to 3. In the next theorem, let x is greater than 0, a dash b dash c, d belongs to c, and real of q2 is greater than real of q1 is greater than 0, real of s1 is greater than 0, real of s2 is greater than 0, s is greater than equal to 0, mod of 1 upon t is less than 1 be such that real of c is greater than 0. Then the following fractional integral formula hold true, which is shown in the equation number 34, where 3f3x is a special case of generalized hypergeometric function. Fractional calculus is very useful in many applications. We conclude our investigation by remarking that the result presented here are the survey of the fractional hypergeometric function. We also presented some new result for Marchev-Saigo-Meda fractional integral involving extended hypergeometric function. Our results have been expressed as a Hadamard product of the extended hypergeometric function and generalized hypergeometric functions. Some special cases of our main result are easily converted by using the interesting known extension of beta function and other special function. So fractional calculus is very useful in many applications, not in sciences but also in engineering. The fact that there is exponential increase in the number of publication on the application of fractional calculus in various fields prove that the topic indeed is very promising. And here are some references of the paper. Thank you.
Thank you, ma'am, for your valuable presentation. Dear participant, if you have any question, please feel free to ask. All of you are permitted to unmute yourself, or either you can put your question in the chat box.
Okay. Shilpi madam, it's really nice talk, and rather that is called a informative session and talk what we can say it. And this is really useful for all participants who work in this, especially the field of fractional calculus or the special function both. Okay, and particularly in the mathematical physics. Nice for valuable time to spare us and to deliver your talk. Thank you, madam.
Thank you so much, sir.
Professor Maher, please present the certificate to Professor Shilpi. Yes.
Thank you, ma'am, once again. And the certificate is awarded, proudly awarded to our resource person, Dr. Shilpi Jain, from the Department of Mathematics, Purima College of Engineering, for imparting our valuable thoughts in international training workshop on computational special function and their applications. Thank you very much, ma'am, for your valuable time and very informative session. This was for all the participants.
Thank you so much, sir.
Thank you, all of you. And once again, I ask you to all the participants, please open your webcam so that we can have a screenshot for this session. I request kindly open your webcam to all the participants.
Professor Meher, please announce regarding the our session 132, and then
Yes, sir.
no,
Yes,
2
yes.
o'clock Professor Maman will join.
Please, all the participants, open your webcam. There are still many participants who did not till now open their webcam. Once again, I request to all the participants, please for a short while, open your webcam. Okay, thank you very much. Dear participants, there is a small announcement. We will resume the next session at 1:30, and resource person will be available at 2 p.m. But we will start the next session at 1:30 p.m. So there is a break for about 30 minutes. Thank you very much, all of you, and stay connected. We will resume the meeting after 30 minutes.